Welcome to this video. Welcome back if you came from part A, so the no calculator portion of this AP Precalculus practice exam. That's always hard to say, Precalculus practice. It's a tongue twister. But anyway, we are continuing to solve the practice exam. This is part B, the calculator required portion. So I'm solving this live. I've never seen these problems before. I have not looked at them even. I have not pre-solved them, so I'm solving them for the first time, like I would for an exam. So hopefully this is helpful to see how I think through the problems. All right. And hopefully I don't make any mistakes, but if I do make any mistakes, hopefully you don't make the same mistakes that I do. All right, so let's begin. The figure shows a swimming pool filled with water. Pump is used to remove water from the pool until the pool is empty. When the pump is running, the rate at which the volume of water in the pool decreases is constant. So maybe that is key. Constant. The rate is constant. Let's underline those two terms. During the first 2 hours, the pump works slower than usual due to a broken piece. Then the pump stops working. The broken piece is replaced, and the pump works at its usual rate until the pool is completely emptied of water. The entire process of emptying the pool takes 6 hours total. Which of the following graphs could depict a situation where time in hours is the independent variable and the volume of water in the pool in gallons is the dependent variable? So T would be the X, independent variable is the X, and the volume of water is the Y. Okay, so the key here I underline, it's a constant rate. Even in the first 2 hours when the pump is broken, it's still pumping at a constant rate. Okay, so actually all these are constant, so that doesn't help us too much in terms of something being non-constant rate. All right, so let's continue. And then the pump stops working, so it should be flat for some point, which all of them are. And then the pump works at its usual rate. Okay, so when the pump works at its usual rate, the rates should be faster than in the beginning when with that broken piece. Okay, so the slope of the line should be different because the rate of change is the slope of the line. Hopefully that sounds familiar. And the rate is change in y over change in x. That is slope. Okay, so that's another way to think about it. So the slope of the later portion should be more steep than the slope of the beginning portion. So this looks like it's pretty much the same. This one's more steep, so it's maybe that. This one looks the same. This one is a lot steeper actually than the beginning. So we can probably eliminate A and C already. Okay, now what about the 6 hour thing? The entire process of emptying the pool takes 6 hours. So they both end at 6 hours, okay? So that doesn't help us. So what is the time? During the first 2 hours, the pump works slower. So during the first 2 hours, it should be slower. This one is the first 4 hours, it looks like it's slower. This one is the first 2 hours, it's slower. So B looks like the best answer. Okay, that's how I would approach this problem. Let's move on. So here, I didn't even need a calculator. Okay. In a certain simulation, the population of a bacteria colony can be modeled using a geometric sequence, where the first day of the simulation is day 1. The population on day 4 was 4,000 bacteria, and the population on day 8 was 9,000 bacteria. What was the population of the colony on day 6 based on the simulation? So the key here is geometric sequence. How do the terms in a geometric sequence relate to each other? So let's call this sequence A sub n. Okay, so where A is the population. Okay, so A sub 4 would be the population on day 4, which is 4,000. Okay, and the A sub 8 would be 49,000. They told us. Okay, so for a geometric sequence, if you remember, A5 would be R, some constant ratio, times A4. The next term, you multiply or divide by a number. That's a geometric sequence. So A6 would be R times A5, which is r squared a4. I just put a5, this definition, into here. So a7 would be, similarly, r cubed a4, and a8 would be r to the fourth power a sub 4. So we need a calculator for this one. Okay, so, but let's plug in. So we have 49,000 is equal to r to the fourth times 4,000. So r to the fourth would be 49,000 over 4,000. Okay, so r would be 49,000 over 4,000 to the, if you don't have a fourth root on your calculator, it's to the 1/4 power. So what is that? Let me plug it into my calculator right now. I'm just using the app on my phone. So I'll even show you 49,000 divided by 4,000, okay, to the 1/4 power, which is 0.25 power. Okay? So R would be this number, 1.8708 something like that, okay? So we even have, I don't know if I showed that, so that's my, I don't know if this is in focus either. Okay, so that's my R. So on the 6th day, we even wrote right here already, it's r squared times a4. So let's directly use this guy. Okay, we're going to square it times a4, which is 4,000. So our answer should be 14,000. Answer is C. Okay, so once again, we found what the common ratio was in this geometric sequence because we were given two terms in the sequence, so we can easily find the common ratio. Okay, and then we use this common ratio to get the population on the 6th day. So we just multiply the ratio to a4 twice. So a4 times r squared, which is this guy. Sorry, the video got cut. I had to attend to something in person. But we are on 78 now. The rate of people entering a subway car on a particular day is modeled by the function r, where r is this guy, for t is between 0 and 20. R of t is measured in people per hour, and t is measured in hours since the subway began service for the day. Based on the model, at what value of t does the rate of people entering the subway car change from increasing to decreasing? Okay, so the best way to go about this is probably to graph this. So I have it in my calculator already. Looks something like this, between 0 and 20. So they're asking when r, which is the rate of people entering the subway, when that rate changes from increasing to decreasing. So basically, the function increases here, and then it decreases here. So we want this point, this maximum point, because that's when the function changes from increasing to decreasing, which is exactly what is asking. Not from decreasing to increasing, that would be this minimum over here. But we want this maximum over here, because once again, it's from increasing to decreasing. So what's that value? That is at 5.505. So that is D. #79, the table gives values for a function m at selected values of t, which the following graphs could represent the data in a semi-log plot where the vertical axis is logarithmically scaled. This is always hard for me to say. Okay, so let's see even the points first. This is 30, 50, 80, 139, 231. Okay, so this is between 1 to 10. So this graph already would not be correct at all because this value would be like, so this would be 2 over here. So all these values from 1 to 3 are between 1 and 2, which clearly is not the case here. Cross that out. Okay? This doesn't look like it's log scale at all. This looks like a linear scale. Okay? Log scale should look something like this, or even this, but this was put in the wrong place. It should be like 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, like that. This looks like it's a linear scale. So cross that out. Okay, this one is also linear scale because it goes 50 to 100, 150, 200, 250. That's a linear scale. As I said, log scale should look something like this or this. Okay, so the final choice is C, and we can even confirm 1 is 30. That looks exactly like that is 30 because this is 10, this solid line here, and then this 20, this is 30. Next is 50, it'll be somewhere there. And then eventually at 4, it should cross 100 a little bit. And then 200 would be this line, so this is a little bit above 200, so it looks like it's C. Okay? That's how you kind of plot it in semilog. Okay, at a coastal city, the height of the tide in feet is modeled by the function h, defined by this guy, t is between 0 and 12, based on the model which of the following is true. So maybe you want to graph this also, so let me show that. Okay. So we want t is between 0 and 12, so my app does it in terms of pi, so it would be around 4 pi, because pi is 3.14, so around 3 times 4, that's 12, so it'll be between 0 and 4 pi, basically. Okay, so the maximum, so h is the height. Is the maximum height of the tide 13.8? Well, we could even use the function. Is it 13.8? Whoops, it is. And we know because it's the amplitude plus this offset. That would be 13.8. So this is good. But let's see the other choices. The answer should be A, and it looks like it is, okay? The maximum height of the tide occurs at t is 6. No, it would occur at t is 0 and t is 12. Okay, so I'm looking at the x values up here. T is 0, this you can round to 0. And we know that also because this is a cosine, so at t is 0, it's at its max. Okay, so clearly not B. The minimum height is 1. Is that correct? It's 1.2. Okay, that's the minimum. Oh no. Minimum height occurs at t is 12. No, that is at t is 6, or x is 6. The answer is A. Okay, let me do 1 or 2 more and call it a part. Probably let's finish this page. Function f is defined by f of x is a sine bx plus c plus d for constant a, b, c, d. In the xy plane, the points 2, 2 and 4, 4 represent a minimum value and a maximum value, respectively, on the graph of f. What are the values of a and d? Okay. So hopefully, even kind of in the previous problem, I even hinted, a would be the amplitude, and d is the offset, or the vertical shift, basically. Vertical, yeah, shift up or down. Okay, so we can even kind of sketch it. If 2, 2 is the min, okay, and 4, 4 is the max, so it should look something like this. This is a sinusoid. Okay, so it should look something like this. Okay? So the average over here is 3. All right, why do I want that average? Well, the amplitude is how much it goes up to the max or down to the min from the average. So the amplitude is 1. So A is 1. Okay, so we eliminate C and D. Okay, now what is this? So choice C and choice D. What is D? That's the offset. So we shifted from 0 up by 3. So the answer would be A. So it was a vertical shift up by 3 because when we have, just for example, sine x, you start from 0, the average value is 0, but the average value here shifted up to 3, so that's why D is 3. And A is the amplitude, is how much it goes up or down from the average to the max or min, so that is clearly 1 as I sketched it. Okay, and actually I'll call it a part here, so please like this video if this has helped you in any way. And also please subscribe if you haven't already. And please look out for the next part where I'll finish these calculator required questions. Actually, a lot of them, we didn't even need to calculate. So yeah, anyway, that's beside the point. Hopefully I'll see you in that video. Bye.